Hello, you beautiful people. So it's again the semi-batch reactor, and this time I want to show you how you can implement the Euler code for the semi-batch reactor with Matlab. So this time it's only the Matlab code, how I did the programming. I will upload the file in the email room, but then afterwards I will do another video where we talk about the results of the simulation. Okay, first I thought of doing the programming like online or like live programming, but then I found out that it took quite a while. That's why I decided I will present you my code. Then I will just give you some commands about the code, and then you can have a look at it on your own. So what was the task? We had the reaction, an acid plus a dicarbon acid plus an alcohol can form a monoester. This is the wanted product. So we want to have a high concentration or a high amount of the monoester. But unfortunately there is a side reaction or consecutive reaction where the monoester reacts with alcohol and forms a diester. The reaction rates are given here. So R1, the formation of the monoester, is as the double the rate constant compared to the consecutive reaction. Then there were some boundary conditions. Overall there were 3 setups. The first one was you start with a fixed amount of acid and you add your alcohol with a constant flow of 4 kilomoles per hour, and this is for 5 hours, and the total reaction time is 6 hours. Then the density was given 920 kilograms per cubic meter, and unfortunately last time I made a mistake. I hope you all received the email about it. I put here not 1 over rho dot the total density, but I just put the total density here. So it must be 1 over the total density. And the same for the concentration, but in the programming we use this one here. Okay, yeah, basically that's it. And then let's have a look at the code that I created. Okay, first I said clear all, like always, to make sure that you don't have some old results stored in your variables. Then I put in all the molecular weights. Then I put in the density, and then what I did here, I said, okay, which setup am I using right now? So setup, I put it to 1, and then I defined, okay, for setup 1 I want to have my alcohol concentration should be 0, and I only start with the concentration of the acid and the solvent, and all the others are 0. And then additionally I put in the 2 molar flows that could be there. So this is n dot alcohol. So the amount of alcohol that you feed to your reactor should be 4, and acid should be 0. For the second setup, I just switched it here. I said, so here now my alcohol is 20 and the acid is 0, and the mole flow is now 0 for the alcohol and 4 for the acid. And for setup 3, this was the pure batch reaction. Here we start with 20 kilomoles of alcohol, 20 kilomoles of acid, and 50 kilomoles of solvent, and the mole flow both of alcohol and acid are both 0. And just by setting this setup variable here, you can set it to 1, to 1, 2, and 3. You can you have all the 3 setups in one file. Good. Then here are the rate constants, 0.4, 0.2. Then the duration of our feeding of one of the educts. Then our total reaction time, 6 hours. Then our delta t, our time step size, 0.1 hours, and I had to put in some initial values. So I said, okay, our first time is 0, T1 is 0, and then I have to put in all our start concentrations. Okay, and basically that's it. Then we can go for the loop where we do the calculation. As I said in the slides, first you have to calculate the volume. For the volume you need the mass inside it, and the mass you get by just multiplying the mole amounts times the molecular weight of each component. So this is the amount of alcohol times the amount of times the molecular weight of alcohol, and then so on. And what you can see here, so for me this makes programming a little bit easier. If you want to have a line break in Matlab, then you can just put 3 dots at the end of your line, and then this goes to a new line. So here you can, for me it's more, it's quite convenient if you just put it here in this layout. Okay, if you know the total mass for each iteration step, then you can say, okay, my volume is the mass divided by the density. So here I put it correctly. You have to divide it by the density, not multiply it. Okay, and then you have your volume. With your volume you can calculate the concentrations. So this is just the amount, the moles, number of moles that you have of each component, and divided by the volume. This should be an I, sorry. Yes, okay. When you have, if you have the concentrations, then you can easily calculate the reaction rates. This is just the rate constant times the concentrations. For reaction 1, it's the concentration of acid and alcohol. For reaction 2, it's the concentration of the monoester and the alcohol. Then I put in an if statement just to see if our time is more than this 5 hours, then your feed to the reactor shall become 0. So I just put in here, if it's more than 5 hours, then it should be like this. Okay, and to get the right time step, it's always a little bit tricky. I have to subtract here 1 delta t. If you think about it, then maybe you can figure it out why. Okay, if you know this, then you can say, okay, let's calculate the change in the number of moles. And in the lecture, I said this is kind of brain work that we need to do here. Okay, what does it mean, our alcohol? Alcohol is consumed in the first reaction and in the second reaction. That's why I put a minus here. Then you have to multiply it with the volume. And you have to take into account that there could be an inflow of alcohol. And that's why you also have to put the n dot alcohol in here. And then in the end, you have to multiply it with the delta t with the time step. For the acid is consumed by the first reaction. This has to be multiplied with the volume. Then you have to take into account that there can be an inflow of the acid, and also multiply it with delta t. For the monoester, there's no inflow, but the monoester is produced by the first reaction and is consumed by the second reaction. That's why it's R1 minus R2. Again, multiplied by the volume and the delta t. Your diester is produced by the second reaction, then multiplied by volume and delta t. And water is produced by both reactions, so it's plus R1 plus R2, and again volume and delta t. Okay, and then you just say, okay, my new mole amount is the old amount plus the change. And only for the solvent you have to do like nothing, so this is not changing. The concentration is changing because your volume will increase, but your number of moles stay constant. Okay, and then you do something with your time. You have to increase your time. Then I gave you the I asked you in the worksheet what is the ratio of monoester to diester. So, and this means at the end of the reaction. And here I put it when the loop is over, then this concentration will be calculated. And since I put here not a semicolon, you will get the result in your shell here. Okay. Then let's go for the plotting. I said figure 1. I clear all, and then I plotted the alcohol concentration. So here you have to take into account your time goes to I plus 1, but your concentration is only calculated up to I. So the size of your vectors is not the same, and that's why you have to say, okay, plot the time just from the numbers 1 to I, and the size of the concentration is just I. So here then the length of the vectors is the same. Okay, and then I did it again for the acid, for the monoester, for the diester, for water and solvent. And since I'm especially interested in the monoester, I said, okay, let's plot this in red. So if you want to have a red line, then just say R. And I said, okay, to make it more, to make it more important, I just put the line width to 2. So it will be a red, bigger line. Okay. Then I put in the location. I think you know this already. I put the X label, the Y label, I put the grid on, and yeah, maybe just let's have a first look. Oh, what's wrong here? 113, I didn't change anything. What did I do? Some copy-paste mistakes. Okay. So figure 1 should look like this. Okay, so I said in the worksheet, I said plot all the concentrations, but if you see it, the solvent concentration, it's really high, and it's you cannot see this in a lot of detail. So let me just comment this, that we might see a little bit more. Okay. So it should look like this right now. Okay, what else did I do? I said, okay, let's put a second figure. There I just plotted the number of moles. So nothing special about it, just a different plot. Then I put in figure 3, I put the reaction rate to have a look at the reaction rates, and in figure 4 I just put the ratio of the concentrations of the monoester to the diester. Okay, then let's have a look at all 4 figures. Okay, what you can see here is that your reaction rate is quite high for reaction rate 1. So this is the production of the monoester, and in the beginning the second reaction is quite slow. But then since our amount of acid is decreasing, the reaction rate is going down, but we still have a lot of alcohol and we have a lot of monoester, so that's why the reaction rate for our second reaction is going up. Okay. So hopefully this should work fine. If we go here and say, okay, setup setup 2, then you can see that some things changed here. For example, the ratio changed from nearly 3, it changed to 1.65. So if you are interested in a high amount of monoester and a low amount or low concentration of the diester, then you can see that it's not working quite well. But I will do a different video about the results. I just wanted to show you here how this is working, and I think with this Matlab code you can simulate a semi-batch reactor. Okay, then don't forget to save it, and then basically you're done. Okay, all the best and bye bye.